Logarithms, solving equations. When you have equations with logarithms or exponentials, then you need to identify the best method to solve the equation. If the equation is in exponential form, b to the y equals x, where the exponent y contains the variable or variables, okay? That's what you're trying to solve for, is the exponent. Then the first thing you try to do is you write both sides of the equation as the same base to a power, right? If this is not possible, then rewrite the equation in logarithmic form to solve. This is also accomplished by taking the log of both sides. That's actually in the book I currently teach out of, and I've seen it in other books, and many teachers do that. But since I already teach you how to rewrite these things, then I choose to solve these problems in a way I've already taught you to do, as opposed to introduce something new of taking the log of both sides. All right. If the equation is in logarithmic form and you have verified all the bases are the same, then here's what you need to do. Condense all logarithms to a single log with a coefficient on one side. So that means you get all your logs on one side of the equation and everything else on the other. And then simplify all the logs down to a single logarithm with a coefficient of 1, which there's a video for that as well. Rewrite the equation in exponential form. So we're going to change it. All right. So note, there is one exception. When every term on both sides of the equation is a logarithm, you may condense each side of the equation to a single logarithm with coefficient 1. Then you may set only the arguments of the logarithms equal. So if I have log base 6 of something equals log base 6 of something, if they're both log base 6, I can just drop the logs and then boom, I can set the rest of it equal. All right, and I have an example of that in here as we work through them. So here, let's go through these, and we have exponential form right here. Solve if the solution involves logarithms, give the answer rounded to 3 decimal places. Okay, so if we end up with a logarithmic answer, go ahead and punch it in the calculator and let's get a decimal approximation. So 7 to the x equals 343. So can I write 343 as 7 to a power? If I can, or if I can write 7 and 343 as the same number to a power, then I can solve it that way without involving logarithms. So here, 7 to the x equals 7 to the third power. 7 to the third power is 343. So now, since the bases are the same, then I can just set the powers equal, okay? So that means I can just get rid of the 7 and say x equals 3, right? If 7 to one power equals 7 to another power on the other side, then the powers have to be equal because you're raising 7 to that on both sides, right? So then x equals 3, and then you would solve this, but this one is already solved. That one is already solved. We don't need to solve anything. X equals 3 is already solved. All right, 2 to the 4x minus 1 power equals 8. Can I write 8 as 2 to a power? Yes, I can. So 2 to the 4x minus 1 equals 2 to the third power. Now, sometimes you can't write one side as a power to the other, or the other side, they're the same base is what I'm trying to say. You can't take the 8 as 2 to a power, but you can change both of them to the same number to a power. And sometimes you can't do either, and we'll address that as well. So here, again, the 2's are the same, so we just get rid of the 2's, okay? And we get 4x minus 1 equals 3. We just set the powers equal. And then we solve. In this one we have some work to do, but not a lot. So we're going to add 1 to both sides. We get 4x equals 4. Then we divide both sides by 4 and we get x equals 1. X equals 1, right? And solving that is something that hopefully you know how to do a linear equation solving pretty quickly. All right. If you don't, you need to definitely go practice that. That needs to be like breathing. You don't think about breathing, you just breathe. Okay? So it just needs to happen. You need to look down and go, oh, I have a smart hand. 4 to the x equals 32. Can I raise 4 to a power and get 32? Well, not a whole number power, but maybe I can, I don't want to get into fractional exponents. We could rational, but what I think I want to do here actually is see if I can write both of them as some other number to a power. And I note that 32 is 2 to the fifth, and also 4 is 2 squared, but 2 squared is all raised to the what power? The x, right? The 4 is raised to the x, and then I need to raise, if I change the 4 to 2 squared, then all of that needs to be raised to the x power. And that matters because now I have over here a power to a power. So I don't have yet 2 to a power equals 2 to a power. I have a little work to do. This is 2 to the 2x, right? If we raise a power to a power, we multiply those, so we just get 2x. And that equals 2 to the 5th power. Now we can get rid of the 2's, and we have 2x equals what? 5. And then we solve this, divide both sides by 2. X equals 5 halves. X equals 5 halves. So e to the x plus 1 equals 1 over e. Okay, don't let the e's confuse you here. Can you rewrite one side or both sides as the same number to a power? Well, you have e to a power on the left. Can I change 1 over e as e to a power on the right? Well, sure I can. How do I bring this up to the top, to the numerator? I change the exponent from positive to negative, so it's going to be e to the negative. It's understood to be 1, so this is e to the negative 1, and then over here this stays e to the x plus 1. So when I bring the e up to the numerator from the denominator, right, it's in the bottom, it's in the denominator, I bring it up, then the power changes from negative to positive. Since it was a positive 1 in the denominator, it becomes a negative 1 in the numerator. And now I can get rid of the e's, right? And I can set the powers equal x plus 1 equals negative 1. And then here to solve, you subtract 1. That's not 1. Subtract 1, and you get x equals negative 2. X equals negative 2. All right, so I'm trying to show you different scenarios you may run into here where you get a fraction or you get a negative, or you need to use a negative exponent, or you need to rewrite both numbers on each side as something else to a power, right? And then here I literally said, what is the craziest thing I can think of, right, to give them? And you look at this and go, oh, I believe it, right? I mean, 25 and then the exponent is x squared over 2 minus 3x. Are you kidding me? And then on the other side equals a fraction 1 over 125, and then that exponent is x minus 4/3. Wow, we got halves and thirds. Don't worry, we don't have to get a common denominator yet, okay? But we may at some point. So first, can I rewrite 125 as 25 to a power? Well, with fractions I can, but what about, is there another number I can do and just use whole numbers and not fractions, or integers I should say, because it might be negative. All right, so yes, 5, right? So 25 is 5 squared, and then that's all raised to the what? X squared over 2 minus 3x, and I'm going to put that in parentheses. Well, I don't have to here. That's the power. It's all raised to that power. And then equals, here, this is 5 cubed, but if I move it to the numerator, guess what? It's going to be 5 to the what? Negative 3. And then x minus 4/3, right? This is really 5 to the third, and then when I bring it up, it becomes negative on the exponent, okay? So I took care of the negative inside there with the 5 to the negative 3, and I didn't have to worry about that x minus 4/3. Now, again, I have a power to a power, so what do? I have to multiply these things and multiply these things. So this is going to be 5 to the 2 times x squared over 2 minus 3x equals 5 to the negative 3 times x minus 4/3. Good gracious. Wow. All right. So now I have 5 to a power equals 5 to a power. If you wanted to simplify the powers first, you could. But here I have 5 to a power equals 5 to a power. So I can drop the 5s, and I can go to 2 times x squared over 2 minus 3x equals negative 3 times x minus 4/3. All right? Now I left this whole board for a reason, because I'm going to need to move over and use a whole nother column over here. Now I'm going to show a step here that you may or may not need to show here. All right? But again, let's talk about skipping steps again. If you skip steps and you continually miss problems, don't skip steps. You're watching this video because you need help in algebra for a test, most likely, whether it's Algebra 2 in high school or Algebra 1, or whether it's intermediate or college algebra in college, or some other pre-calc something. You're watching it for a reason. You're not just sitting around going, ooh, let me watch math videos because that's fun. Nobody does that. I know that. All right? I put these out there to help you. So let me show you the step that's happening here. I want to, what I call, show the distribution, okay? I'm going to show the distribution on both these. So I'm going to come up here and show my distribution. So when I say that, I'm going to say 2 times x squared over 2 minus 2 times 3x. So I'm showing the 2 times each thing. When it's a fraction involved, I do that a lot of times because it's just easier to understand. If you can do that without it, that's fine. But if you're skipping it and missing it, don't skip the daggone step. All right? So equals negative 3 times x, and then minus negative 3 times 4/3. So I'm putting my minus sign here, and then I'm taking my negative 3 and putting it here. Okay? You with me? You see what I did there? And then I did the same thing over here. I did my minus sign here, and then my 2 here. Okay? I just didn't need parentheses there because I was minus and then 2. So now we showed the distribution. Put this over 1. The 2's divide out. We're left with x squared. Okay? We're left with x squared. And then here, minus 6x equals. Okay? Here, minus 3x. And then what's minus and negative really mean? It means plus. Plus, and this is really over 1. The 3's divide out, and I'm left with plus what? 4. Right? These things become 1. 1 times x squared is x squared. These become 1. 1 times 4 is 4. And you get plus because you have a negative times a negative. Now I have a x squared, and the way we solve x squared typically is we get everything on one side equal to 0, and we first try to factor it. I would rather do that than the quadratic formula or something else first. I want to try to factor it, okay? So I'm going to add my 3x to both sides. And then I'm going to subtract 4. Now, I don't really have a place to put it. I'm going to put it under the x squared, but these don't go together, right? I'm just writing it over here somewhere. I didn't really have room to put it somewhere else. So these things cancel on the right. And then on the left-hand side, I'm going to put things in descending order because that makes it easier to factor. Start with x squared, and then those two terms do go together, right? They combine. They're like terms. So negative 6 and plus 3 is negative 3, and we get a like term. When you add or subtract like terms, combine like terms, you get a like term. So what I mean is if I put x's together with adding and subtracting, I get an x. I don't get anything else. And then minus 4, right? I got to tack this on here. For descending order, I'm putting it at the end. So x squared minus 3x minus 4 equals 0. Now how do I solve this? Well, try to factor it. X and x. If you have trouble factoring, go watch my list method video. That's what this would be. I have other factoring videos as well, but the list method is what this one is. All right, so then we have the factors of 4 that subtract to give me 3, and I'll come back to the negative. So it's either going to be 1 and 4 or 2 and 2. Well, 4 minus 1 is 3, so let's put in here the 4 and the 1. And then the signs are different. The bigger number gets a negative. So bigger number's 4, so it gets the negative, and since they're different, the 1 gets a positive. Okay? And then what do? I set each one of these equal to 0. Set each one of these equal to 0. X equals 4. And then x equals negative 1. So x equals 4 and negative 1 for those where there's 2 answers here. Right? The x squared, 2 answers here. So if you plug 4 into that for x, you're going to end up with a true statement. If you plug negative 1 in for that, for x, you're going to get a true statement. All right. So let's see what we have next here. And again, this one is not really all that basic. This would be more of an advanced type. But I wanted to show you one that was just crazy. I just said, let me come up with something really, really crazy. All right. So I started writing and calculating and all this other stuff, and 10 minutes later I come up with this one. All right, really not 10 minutes, maybe 3 or 4, but still. All right, 10 to the x equals 8.07. So this is the same scenario. We have this exponential, and we're looking for x. The problem is I can't write 10 and 8.7 as the same number to a power. I can't definitely write 8.7 as 10 to a power. So when I look at this, if this number is 10, then it makes the most sense. Well, actually, I'm going to rewrite it anyway. I'm going to use the log, okay? I'm going to use the log here. So what I'm going to do is I'm going to rewrite this thing. So it's going to be log, and we start with the base, and we go across the equals what's left. So log, and if I go base 10, I go, oh, wait a minute. I don't need to write the base. It's understood to be what? 10. So just log of 8.07 equals x. Okay? And here's where I said if you have a logarithm, approximate to 3 decimal places. If your teacher says give me exact answers, I'm going to give a high five to your teacher because I love exact answers. The one thing about plugging it in your calculator and getting an approximation, you kind of learn what log of 8.07 is. Because if you were an engineer, or if you were a scientist, or if you were a mathematician and you were doing something in the real world, because there are problems in the real world that involve logs, okay, then, or square roots, or something else, you would put them in the calculator and you would get a decimal approximation, okay? One of the things that I personally have seen is at a vehicle factory, I took a group of students to one time, and there was a robot that machine cut some kind of bolt for the vehicle. And when it machine cut the bolts for the vehicle, it cut it within 1,000th of an inch. Okay? And that was its margin of error. And as long as it cut the bolt within 1,000th, this is the threads of the bolt, within 1,000th of an inch, then the bolt fit. And so they would sample to make sure, and if they found some bad ones, they'd have to take them out and test more of them. But, with all the technology we have now, those machines can just roll. All right? But that's what happens. They didn't say, we'll do the log of 8.07. They found the decimal and said, here, we got to get within 1,000th. We got to get within 3 decimal places. Can't be any different past, it can be different past 3 decimal places, but not up to. All right? So here, if we take this and we have 8.07 and we take the log of it, then we get 0.9068. So 0.907 to 3 decimal places. Okay? 9068, and the 8 says, hey, take the 6 and go up to 7 for 3 decimal places. And if you wanted to put the 0 in front, that's okay. When the 0's out in front of the decimal, it's negotiable. Write it or don't write it. It's when there's a 0 after the decimal that's not negotiable. Right? That's got to be there. All right, so for the next one, I'm going to rewrite this one, and I'm going to say, okay, log base E. Wait a minute, right? I'm going to go here across and equals this. I'm going to go, wait a minute, log base E. I don't need to write log base E. That's what? That's ln. ln of 5.7 equals x. All right, ln of 5.7 equals x. So what I've done here on this page is I've given you a 10 to a power and an e to a power. If you have 10 to a power or e to a power, when you rewrite them, you just get log or ln. You get the common logarithm or the natural logarithm. You don't get log base 6 or log base, whatever. You get log understood base 10 or ln understood base e. So when you write log base e, when you're rewriting this, go, wait a minute, that's ln. That's ln. So ln of 5.7. So let's say here 5.7. ln of 5.7 is 1.7404. So 04 says keep it at 0. On that, put that 0 there because we're told to go to 3 decimal places. If your teacher tells you to go to 3 decimal places and you just put 1.74, you didn't follow instructions. All right, so be sure you do what they say, right? You're in their class trying to earn points and not get points taken off. All right. So e to the 4x equals 7. So now we're adding a little bit. We're not just have x for the exponent. In the next one we even add more stuff. So here, e to the 4x equals 7. So again, if I rewrite it and I go log base e, wait a minute, that's really what? ln, and I go e across here, right? The base to the other side across the equals, right? Equals what's left. So ln of 7 equals 4x. But I don't want 4x, so I divide both sides by 4. Divide that out. So ln of 7. Now notice, this is not this. You cannot do this. No. Right? You divide all of ln of 7 by 4. And so how you put that in the calculator is going to be important as well. You need to find the ln of 7, whether that's ln 7 close parentheses or 7 and hit the ln button depending on what you're using or whatnot. If you have a graphing calculator, you can just type it in ln. It should open the parentheses for you. 7, close it, divide it by 4. But you got to close the parentheses before you divide by 4 if you have one of those calculators. Okay. So here, the ln of 7 is about 1.9459. And I divide that by 4, and I get 0.4864. 0.48, and then I get 64, and the 4 says keep the 6 there. I'm up the 0 in front. It doesn't matter. You don't have to. It's negotiable. So 0.486. It's the ln of 7. The ln of 7 divided by 4. Right? So what about the next one here? What about the next one? Well, 4e to the 7x equals 10,273. Well, I need e to a power. I don't like that 4 there. That 4 messes me up if I try to rewrite this. I need an exponential here without the 4 there. So I need to divide both sides by 4. So then e to the 7x equals, and I'm just going to leave it this way right now. Now this particular problem, when you divide by 4, think about 4 quarters in a dollar. You either get 0.25, that's like 25 cents, 0.5, which is 50 cents, 0.75, which you either get one of those 3 that terminates. So if you divided this one and wrote the decimal down, that's fine. But if you had a third, you couldn't just write 0.333. You need to leave it 1/3 when you plug it in the calculator. You don't want to start rounding until the very end. You want to plug everything in like it is and then only use the last value rounded. Don't round and then key it back in. Because even though your calculator may show you even 16 decimal places, it probably goes out to 128 decimal places or something. Maybe further than that. Who knows? But it goes much further than it shows you. I can guarantee you that. All right. So here, e to the 7x, and then so if I rewrite this, log base e, in my mind I'm saying it, I'm not writing it. Log base e is what? ln. ln of the other side, right, equals what's left. So 1,273 over 4 equals 7x. And then we divide both sides by 7. So then x equals the ln of 10,000, not 1,000. 10,273 divided by 4 all over 7. So on my little, I'm just using a little basic scientific here. So I do 10,273. I hit ln. No, I don't. I hit divide by 4. Sorry. Equals. I get 2568.25. So this becomes 2568.25. And this one's exact. So I mean I can show you exactly what it is. Then I hit the ln button and I get 7.85. This whole numerator is like 7.85. And then I divide that by 7, which is going to be a little bit bigger than 1. This is going to be 1.12, and then it's 1.5. That 5 says take that 1 up to a 2. So it was 1.1215, so it's 1.122. The 1.5 says take that 1 up to a 2. All right, so 1.122 to 3 decimal places. All right. 8 to the x equals 17. 8 to the x equals 17. So here again, I can't write 8 and 17 is the same base to a power. So I need to rewrite this thing as a logarithm. So I'm going to say, start with the base, across the equals what's left. So log base 8 of 17 equals x. If you have a calculator that allows you to input the base, then you can key that in. If you just have like a TI-30X2S, okay? That's just your basic little TI scientific calculator. It only has LOG and LN to my knowledge. I don't think they've added the where you can enter the base in on that one. Okay? So what I'm going to do is I'm going to change the base. So my change of base formula, I'm going to do ln of this over the ln of the base. So ln of 17 over ln of 8. And if you recall, if you go back and see the more properties video on the change of base, you can do ln or log. I choose ln because that's 2 letters and log is 3 letters. That's really why I choose it. I can write 2 less letters. All right? So, well, and I had a professor in college who said the only real log was ln, natural log. So ln 17 over ln 8 equals x. This is not the ln of 17 over 8. This is the ln of 17 equals, divided by the ln of 8 equals. Okay? So you got to make sure that you do this in the proper order. It may require some parentheses and things like that. So, for instance, in my calculator, I hit 17 ln. And then I hit divided by, and I have to open parentheses and hit 8 ln close parentheses equals. Have to do all those things. So, and then again, if you have a graphing or something else, you can do ln 17 close parentheses divided by ln 8 close parentheses equals, and it works. So 1.36, and the next 2 are 2, 4. Well, the 4 says leave the 2, right? The 4 says leave the 2. So 2 there. 1.362 equals x here to 3 decimal places. And then 5 to the x equals 3456.78. So, I mean, I can't take 5 and raise it to a power and get 3,456.78. So I'm going to rewrite this just like I just did. Start with the base, go across the equals of what's left. So the log base 5 of 3,456.78 equals x. Well, I don't have log base 5 button on my calculator. If you do, you can key it in this way. If not, change the base. Again, I'm going to use LN, but you can use LOG. If you want to try, you just use LOG on both of these. Where I'm putting LN, you put LOG. Punch that in your calculator, and we should get the same thing. So 3,456.78. LN is like 8.148 divided by, open parentheses, 5, LN, close parentheses, equals 5.0626. So 5.06, and then I have 26. This says take this and go up to 3. Okay? So 5.063, because that was 26 on the last two, equals x. 3,456.78. I'm just going to check it to make sure. Divided by 5. Yeah, 5.063. 5.063. And then 2 to the 3x minus 7 equals 1,023. And I cannot write 1,023 as 2 to a power. It's real close. All right, 1,024. It's 1,024 bytes in a kilobyte on a computer. Okay, it's 2 to the 10th power. It's real close. One away, but you can't do it. You can't write it as that. So I'm going to say base to this side equals what's left. So log base 2 of 1,023 equals 3x minus 7. All right, well, I need to get x by itself, so I'm going to add 7 to both sides. I'm just going to put plus 7. Look, you cannot put those together. No, because the 1,023 is the argument of the log there. So this is going to be, and I'm going to write it this way, 7 plus the log base 2 of 1,023. Okay? Doesn't matter if it's plus 7 or 7 plus that, and that equals 3x. And then I'm going to divide both sides by the whole thing by what? 3. So 7 plus log base 2 of 1,023 over 3 equals x. But when I get ready to plug this in, if I have where I can choose my own base, then I can do this. If not, I've got to change the base. So let's see what that looks like. If I change my base here, it's going to be 7 plus, and I'm going to do the ln of 1,023 over the ln of 2, all over 3, and that equals x. So I have a fraction inside a fraction here. So again, on my little calculator I'm using right now, my little basic scientific one, I am going to calculate the ln of 1,023, not 123, and I get 6.93. I'm going to divide that by the natural log of 2 by using parentheses, and I get 9.99859, blah, blah, blah. I'm going to add 7, and I get 16.998 something, and then I'm going to divide that by 3 finally, and I get 5.6661, so it stays that way. Not finding that number, but anyway. All right, 5.666 there equals x to 3 decimal places, because the fourth decimal is 1, and it says keep that last 6 a 6. All right. So that one was, right, a little crazy, but that's okay. We need to know this kind of stuff can happen, right? Where we have this log and we have to, add or subtract a number and divide by a number, and I mean, it can even get crazier than this. Log base 5 of x equals 3. Well, look, write it as a single logarithm with a coefficient of 1 on one side of the equation. That's already done for me, right? Here's my single log, coefficient 1 equals everything else on the other side. So here, rewrite it as an exponential and try to solve it. So 5 to the what power equals this, right? Base to the other side equals what's left. 5 to the third power equals x. In my Logarithms, the basics video, I talk about how to rewrite these. Okay, change the form from logarithmic to exponential if that's giving you a little trouble. 5 to the third equals x. So 5 to the third power is 125, and that equals x. The only thing you need to do in this case, not the only thing, you need to make sure that if I plug 125 in, I'm taking the log of a positive number. If you remember, what you take the log of has got to be positive. The base also has got to be positive, and it cannot be 1. What you get, the answer you get on the right side where the 3 is, that can be negative. That can be 1, negative, 0. It can be anything. But what you take the log of has got to be strictly positive, and then the base has to be positive, and it also can't be 1. So then the next one is in the same boat, right? It's just a little bit more complicated, but it's the same boat. You have a single logarithm of 1, coefficient of 1, and everything else on the other side. So we're going to rewrite this. 7, right, base to the other side of the equals what's left. So 7 to the second equals 2x minus 5, or 7 squared, all right? But 7 to the second is the same thing. So now solve this. Well, the first thing I need to do is exponent. So 7 squared is what? 49 equals 2x minus 5. And then we're going to add 5 to both sides and start to say subtract. It's the opposite of subtract. 54 equals 2x, and then we divide by 2. And 54 divided by 2 is 27. And again, I want to make sure if I plug 27 in, 2 times 27 is 54 minus 5 is positive. If you wanted to go all the way out and check it completely, that's not a bad idea. The main thing I check for is, hey, am I taking the log of a positive number? Because if I'm not, I have to throw it in the trash. But 27 works out, okay? 27 works out. All right, here, natural log of 4x plus 1 equals 5. Natural log, wait, what? Natural log of 4x plus 1 equals 5. All right. So what's the base understood to be? Remember, it's e. So what I'm going to do is base to a power equals this. So e to the 5th equals 4x plus 1. Well, subtract 1. So e to the 5, and then the whole thing minus 1 equals 4x. And then we divide by 4. And e to the 5th minus 1 over 4, equals x. Now, if I didn't put this earlier, I wanted you to give decimal approximations for something like this, too, if you have e to a power. So e to the 5th minus 1 over 4 is a great answer. I would love that answer. It's exact. All right? But if I were cutting bolts for Toyota or Nissan or Chevrolet or Ford or some car company and it had to fit perfectly, then I would need to have decimal approximations and have my machine, right, to be within 1,000th of an inch or whatever when it did the thread. So here, e to the 5th, so e to the 5th is 148.413. We subtract 1, so 147, and then we divide by 4. And we get 36.853. 36.853. So the answer didn't involve logs there, but it had e to a power. So if we have something that we don't know, like if that was 2 to the 5th, we could do that, right? But e to the 5th, well, we don't really know. So that's why it's a good idea to punch it in correctly and get a good decimal approximation so we kind of know, hey, this is 36.853, whatever units it happens to be. Log base 6 of x plus 3 plus the log base 6 of x plus 4 equals 1. Here, I don't have a single logarithm, right? I have 2 logarithms on the left-hand side equal 1. So I need to combine these 2 logarithms to a single logarithm. How do I combine logs? Well, if you recall, we have the rule log base b of m plus log base b of n equals log base b of mn. Okay? Remember, if you add 2 logs, then you take the log of multiply these arguments here. All right? That's what the rule is. That's in my more properties of logarithms video. Okay? Sorry, there was something on the screen there. All right, so then log base 6 of this. So how do I put these? We multiply them. So log base 6 of x plus 3 times what? X plus 4. And it's a good idea to make sure there's no doubt. I'm going to put brackets around all of this. That tells me I'm taking the log of all of this stuff here. Okay? Taking the log of all of that stuff. And that equals 1. So now I have a single logarithm with coefficient 1. And some people say, well, why don't you simplify inside the log? Well, I just said get a single logarithm of coefficient 1, and if I need to multiply this out later in there I will. But right now I need to do this. So 6 to the first power, right, base to the power equals what's left. So 6 to the first power equals x plus 3 times what? X plus 4. Now I got to figure out how to solve that. That's what I have to figure out how to solve. So 6 to the first power is what? That's just good old 6. Good old 6 equals, and over here I'm going to FOIL. First, outer, inner, last. So x times x is x squared. X times 4 is plus 4x. 3 times x is plus 3x. And then plus 3 times plus 4 is plus 12. Since it's got an x squared, get it equal to 0. Right? If it was just x, you would get x's on one side and numbers on the other. Linear, right? But when it's a bigger power than 1, we typically get the x squareds on one side and numbers on the other, and then we decide what to do. Okay? So here, I know I need to combine these terms, and look, I already have 12 over here, and it's not going to have anything happen to it, so and the only thing I have over here is 6. Let's go ahead and move it over. I know we're doing 2 steps at once here, but let's go ahead and move it over. Subtract the 6 from both sides, so then that's going to be 0 equals x squared plus 7x plus 6. Now we have descending order equal to 0. Try to factor it. It may not factor, and if it doesn't, we have to use some other method, but I sure hope it factors. I sure hope it factors. Okay? I mean, I want it to factor real bad, right? Because that just makes it simpler. So x and factors of 6 that add to give me 7. 1 and 6 or 2 and 3. 1 and 6 add to give me 7, right? And the signs are both positive. So plus. And then, let's come up here because I'm running out of room. 0 equals x plus 1, or 0 equals x plus 6. Subtract 6 from both sides. So negative 6 equals x. And over here, subtract 1 from both sides. Negative 1 equals x. Now remember, we can't just assume these answers. We have to at least make sure what we're plugging in, we're taking the log of a positive. So if I plug in negative 1 right here, negative 1 plus 3, that's 2, right? That's positive. That's okay. If I plug in negative 1 here, right? That's negative 1 plus 4 is 3. That's positive. That's okay. So negative 1's okay. That one checks out. So now let's plug in negative 6. Negative 6 plus 3 is minus 3. That doesn't work. It doesn't matter what happens over here. I don't care. Because it's no good over here, so therefore it's no good. It's no good. So I have to take this one and say, nope, can't have it. So the only answer I get is x equals negative 1. All right, negative 1. And the reason is I cannot take the log of a negative value, and that's what's happening here. If I plug in negative 6, I get a negative here. Or if you plug it in here first, you get a negative, but you don't have to plug it in both. If you get a negative at any point, it's no good. It's no good. All right? Log base 8 of 5x minus 1 equals log base 8 of x plus 19. Here I have a single logarithm coefficient of 1, but I don't have it on one side. I have it on both sides. So remember that note that said, here's the one exception. If both sides are a single log, if every term on both sides contains a log, then get both sides as a single log coefficient 1. Well, every term has log, and it's the same base. And guess what? I actually already have one coefficient out front and a single log on both sides. So if that's the case, just like we did the powers, 7 to the x equals 7 to the third. Well, here, these two things are the same. So guess what? We can just get rid of them. We can just get rid of these right here. And we can say 5x minus 1 equals x plus 19. If the log has the same base on both sides and it's a single logarithm with coefficient 1, in this case they're both log base 8 with 1 in the front, and we don't have multiple logs, we're not adding, subtracting logs, or dividing logs, anything else, we can get rid of the logs, set the arguments equal. So here this is just a basic, just subtract x from both sides, and I'm also going to add 1 to both sides. Do 2 steps at once. 4x equals 20, and then divide both sides by 4, and x equals what? 5. Now before I circle that answer, I need to make sure 5 times 5 is 25. Is 25 minus 1 positive? Yep. And then 5 plus 19, is that positive? Yep, it is. So that works out. That works out. So we just want to check and make sure it's positive there. So then this is my final answer. All right. So I hope this helps you out with solving equations that are either exponential in form or logarithmic in form. All right. We don't always use a logarithm to solve these. All right. But we need to know that how to identify what to do, and then that's at least half the battle. So hopefully I've helped you with identifying what to do when you see it, and then when you identify what to do, actually completing the solution to the equation.